This is sinc omega over 2 or something like that. Okay? And I said it depends on the definition. Let me explain what I mean by the definition of a sinc. Normally, this function, let's call it sinc of x, is equal to sine pi x divided by pi x. Okay, this is the most accurate description of a sinc function. All right, and therefore, for example, when I say sinc t, it means sine pi t over pi t. This is what I mean. And over here, there is a problem. I have to admit it. When I say sinc omega, it looks like sine pi omega divided by pi omega, but it's not sinc omega. In fact, it is sinc f that I'm talking about. And we know that omega is 2 pi f. So what is sinc f? That is sine pi f over pi f. And notice that 2 pi times f is omega. Okay? So this is sine omega over 2 divided by omega over 2. Because, as I say, omega is equal to 2 pi times f. That's why I deliberately put a t1 equals 1 over 2 for this thing. Okay? So don't get confused about it. Whenever you encounter a sinc function, it's the best to assume that if it is sinc t, for example, it is sine pi t over pi t, and it is sinc, if it is sinc f, then it is sine pi f over pi f, which is equal to this. Okay, that's the accurate definition of sinc. Let's use that accurate definition of sinc again in another example. This time we have seen quite a few examples regarding Fourier transform. Let's evaluate the inverse Fourier transform this time. And notice that the integrations are quite similar to each other. In one case, we have e to the minus j omega t for the Fourier transform. And for the inverse Fourier transform, we have e to the plus j omega t. That's the basic difference. Now, I'm giving you the Fourier transform, and I will be asking you the time signal. And that is equal to 1 for frequency less than w, and 0 and frequency is greater than w, or else you can say. Now what is that? As I say, whenever I give you an expression in an arithmetic form like this, it would be best to first visualize it, to plot it. It says that on the frequency axis of omega, between minus w and plus w, it is ones, and out of it, it is zeros. So it is the definition of a perfect low-pass signal, or a low-pass filter if it's a filter. So this is the low-pass signal in its most pure and perfect form, described on the frequency axis. So what is x of t then? X of t was equal to, there was a 1 over 2 pi, a scale, and the integration was from minus infinity to infinity, x of j omega e to the j omega t d omega. Now, this integration, because of the definition of x of j omega to exist only between minus w and plus w, forces this integration limits to start from minus w and end at plus w, because beyond these boundaries it is all zeros. X of j omega is all zeros, and within these boundaries x of j omega is 1, nothing. So we have 1 times e to the j omega t d omega, and this integral, I have erased it and I'm overwriting it, sorry about that, is the same integral as we did, what we did, right? At least similar. The previous one was in terms of dt, and it was from minus t1 to t1. This is in terms of omega, and it's from minus w to w. So it's the same integral, and the output for this case is quite simple in form again. Like this. Sine omega t over pi t. And it is also known as a sinc signal. But as I say, the sinc signal, sinc t over here is sine pi t over pi t, whereas this is sine wt over pi t. So how do we normalize all these things? They can all be normalized like this. It is w over pi sinc wt over pi. It's a new definition. And how can we get rid of such a definition? I mean, what's a good way to simplify this, to make it sinc of t? It happens when w is equal to, this band limit is precisely equal to pi. When w is equal to pi, this becomes 1, and w over pi will become 1, and it will be sinc t. So it is also obvious from the same expression as well. Whenever this w is equal to pi, it will be sine pi t over pi t, which is sinc t, precisely. That is the best or the simplest way of thinking of it. And our teaching assistant was pointing out how to put legends and draw a sinc function. Let me briefly indicate that one as well. A sinc function, as we have seen, is equal to 1 at t is equal to 0. It is pi over pi at t is equal to 0, and that makes 1. So it is a 1 here, and then it decays, and then starts oscillating and decaying. Like this. Of course, it extends to plus and minus infinity from both sides. The oscillations or the ripples decrease, but they never end. Okay. This point corresponds to the first zero crossing. And when does the first zero crossing of sine pi t happens? When the angle is equal to pi, sine of pi is equal to 0 again. So that is when t is equal to 1. The next zero crossing happens when t is equal to 2, then it is sine 2 pi. So this is 2, this is 3, this is 4, and it goes on. And this is minus 1, minus 2, minus 3. So the zero crossings of a sinc function is like this, and the first lobe, this larger lobe, you may say, is twice wider than the other lobes. At this place, it should go back to 0 for a normal sinusoid, but because of division by pi t again, it doesn't go back to 0, and it appears like this. So it's not 0, but it's 1 at this time is equal to 0 point, and all the other zero crossings are equally separated. That's the plot of a sinc function. And using the scaling properties and the scaling properties, scaling in time, it's like sinc of a times t. How do you plot sinc a times t? Sinc a times t is either stretched or squeezed in time, depending on the value of a. And you just have to put the proper time instances where this thing becomes integer multiples of pi. Okay, that's how you should be able to draw a sinc function. And this is nothing but a scale, so this thing will not be 1 anymore, but it will be w over pi. A similar argument exists for frequency axis, omega, as well. So this is how you plot it. It's a very famous shape, as I say. It's sort of a celebrity. And there is a name of the three-dimensional extension of this one. When you rotate this thing around the origin, just rotate it and sweep in 3 dimensions. What will it look like? it will look like a hat. One of the hats will be here, and then the tails of the hats are like the ripples. And it also looks like the ripple on the surface of water when you drop something. Okay, that sort of a thing. Now that hat shape in 3 dimensions, when you rotate it, also has a famous name in Spanish. In fact, it's in Mexican. That's called sombrero. Okay, it's the hats of the Mexican people. The large hats, they sleep under them. That's the shape that you have. And in image processing, that's an important shape because it's 2-dimensional. Now, with respect to these sinks and this new sink shape that we obtain, we make some observations about what the Fourier transform looks like as opposed to the time signal. Now let's start by this one. If you make this thing indefinitely narrow, what would happen? Or let me write the answer that we obtained to the previous question here, because they are dual of things. What was that? It was x of t is equal to 1 for magnitude t less than t1 and 0 for magnitude t greater than t1. And x of j omega was 2 sine omega t1 over omega. This was the Fourier transform. Let's start from here then. Let's make this x of t indefinitely narrow. How do we do that? By making t1 as small as possible. Let's make it smaller and smaller. If we make it smaller and smaller, what kind of an x of j omega shape will you have? This t1 will be a smaller number. So it will be like not sine of omega, but it will be like sine of 0.01 omega or something like that, right? Now, sine of 0.01 omega, what is it periodic with? I mean, when does the first ripple, first zero crossing appear, this point? When omega is equal to what?
1000 pi, 100 pi.
100 pi. So when omega is equal to 100 pi, it makes the first zero crossing. If it is 0.00001, it will be 1 million pi or something like that. So what's going on here? It's like this shape is being extended more and more, wider and wider. This is, the main lobe is becoming indefinitely wider and wider. And when this number is 0, when t1 is 0, it will be arbitrarily small, very sharp and narrow signal. Then when will be the first zero crossing? It will be at infinity. So this shape that you will see will be a constant shape then. Do you remember that if this is an impulse, then its Fourier transform was 1, which never crosses 0. It's like a very wide, too much wide sink shape. So that's usually what you get. If the signal you write here and the Fourier transform you write here, you have this kind of a property. If this is narrow, if it is squeezed narrower and narrower, the Fourier transform becomes wide. And conversely, if you make the signal wider and wider, you make the Fourier transform narrow. That's a duality property that always happens, because when you make a signal narrow, it means you are increasing the frequency. For example, this is a wide sinusoid. Just squeeze it from both sides. This will be a narrow squeezed sinusoid, which one has higher frequency? This one, of course, not this one. What does a high frequency mean? Higher frequency, it means the Fourier transform shape on the omega axis. For example, this is a bandpass signal around these frequencies, and when you narrow down your signal, these things will correspond to higher frequencies. So it will be like this. Higher frequencies, wider. This one is wider than this one. That's the expected behavior. And conversely, if you make your signal wider by stretching from both sides, you are decreasing the frequency. And how do you decrease the frequency? By making the Fourier transform over the omega axis closer to 0, which is by making the Fourier transform narrower. So such a duality exists naturally. In terms of a typical shape, let's consider those rectangular shapes. Of course, I'm not drawing anything accurately here. I'm just trying to illustrate. If it's a wide rectangle like this, then the Fourier transform will be a narrow sink. And as you make it a narrower rectangle, then the Fourier transform will become wider and wider, like this. And guess what? The left-hand side and the right-hand side of these double-sided arrows, it doesn't matter. If this is your time signal, this is your Fourier transform. If this is your time signal, then this is your Fourier transform. Okay? Except for these particular points. Of course, you need to evaluate them separately, but shape-wise, the Fourier transform and the inverse Fourier transforms are the same. Remember that if the time signal is a rectangle, then the Fourier transform is a sink. If the Fourier transform is a rectangle, and then the time signal is a sink. So it doesn't matter which one is a time and which one is a frequency function. It's up to you. But such an attitude always holds. If one of them is narrower, the other one is wider. And regarding the quiz question that we have already seen, now let's see it in a reverse way. Suppose that x of t is equal to e to the j omega 0 t, which is a sinusoid, by the way. It's a pure sinusoid at a particular frequency of omega 0. What is the Fourier transform of it? Now, in order to do this, or in order to solve this thing, I strongly unrecommend that you apply the formula. What was the formula? It was from minus infinity to infinity, x of t times e to the minus j omega t dt. When you put this thing into here, you will soon notice that let me write it like this, e to the j omega 0 minus omega t dt. These can be combined like this, and soon you will notice that there is a huge problem here, because it looks like an indefinite integration whose values are rather difficult to evaluate. As a matter of fact, whenever this omega is different from omega 0, so this is x of j omega, whenever this omega is different than omega 0, it becomes a sinusoid with some frequency, and this is a symmetric integration around 0, and a periodic signal symmetrically integrated will give you a 0. So it is 0 in most places. when omega is different than omega 0. But when omega is equal to omega 0, it is e to the 0 integral of 1. What is the integral of 1 from minus infinity to infinity? It's infinity. It's the infinite integral of 1s, which will give you infinity. So at omega is equal to omega 0, it is infinity. At all other places of omega, it is 0. This may give you some question marks immediately, or you may resemble it with something that we already know. What does it sound like? It sounds like an impulse, right? An impulse has a value of infinity at a certain point, and it has a value of 0 everywhere else. So this must be something like an impulse. But we couldn't evaluate it. So what we're going to do is, we're not going to evaluate it like this. Why? Because in the formulation of the problem, there was a problem. Problematic problem. X of t is equal to e to the j omega 0 t. What is it? It's a periodic signal. And I'm tricking you by asking the Fourier transform of a periodic signal. You must immediately remember the previous chapter. For periodic continuous time signals, we have Fourier series. So we have to start from those Fourier series. What are the Fourier series coefficients of this one? If something is too simple, then students just don't understand what's going on. Yeah. What are the Fourier series coefficients? 1. Which one is that? No, it's not a minus 1. It is only a1. There's no a minus 1. A minus 1 would appear for sine or a cosine. This is even purer than that. Okay, it's this pure sinusoid with only one Fourier series coefficient. A1 is equal to 1, and the corresponding frequency is omega 0 for that thing. There's only one harmonic. What you really need to do is, on the frequency axis, so I'm giving you the methodology to give me the Fourier transform for periodic signals. For periodic signals, first find the Fourier series coefficient and put it on the corresponding frequency, and this was AK, right? Now replace it by the Fourier transform, okay, and make this not a discrete impulse but a continuous impulse, because this is a continuous function now, and discrete impulses were ending or terminated by a dot. Continuous impulses were terminated with an arrow. So put an arrow here. What is the magnitude of that arrow, of that impulse? It is a1 times 2 pi, which is 1 times 2 pi, which is 2 pi, by the way. So this is the Fourier transform, and you can also write it, x of j omega, formulate it like this, 2 pi times delta omega minus omega 0. This is how we are supposed to give an expression for the Fourier transform. Let me give another example about that, because sometimes, sorry, since Fourier transform is available for a general class of signals, it must include periodic signals as well. So if you have periodic signals, forget about this formula. Just find the Fourier series coefficients. Assume that the Fourier series coefficients that you find are like this. Or assume that you find A0, A1, A2, A3, etc. Some Fourier series coefficients. And this is at omega is equal to 0. This is at omega 0, the fundamental frequency. This is 2 omega 0. This is 3 omega 0. Isn't that true? Then on the frequency axis, you draw x of j omega like this. A0 is this much. Multiply it by 2 pi and put an arrow here. This is 2 pi A0. And then this is 2 pi A1 at omega 0. 2 pi A2 times A2 at 2 omega 0. 2 pi times A3 at 3 omega 0, etc. It also appears for minus A1, A minus 1, A minus 2, etc. They are also valid for them. So find the Fourier series coefficients and insert impulses there. The magnitudes of the impulses are proportional to the Fourier series coefficient value and obtained by multiplying that value by 2 pi. And the corresponding location of the impulse is at the corresponding harmonic frequency. For A2 it is 2 omega 0. For A3 it is 3 omega 0. That's how you should do it. So remember all the examples and questions we did for periodic continuous time signals. We found their Fourier series coefficients, right? And at the back of that chapter there are several find the Fourier series coefficients questions. Convert every one of them to find the Fourier transform of these signals. And what you really need to do is quite simply find the coefficients, locate them as impulses, multiply their values by 2 pi and insert impulses over there. So whenever you have a periodic signal, your spectrum, which is x of j omega, the Fourier transform is your spectrum, is consisting of impulses. And from the linearity, let me keep this question. Some other terms could appear as well. For example, suppose that this is your Fourier transform. What is the time domain signal corresponding to that? Yeah. This one, we already know. It's this rect signal, rectangular signal. This one, it corresponds to a periodic signal because there are impulses. Where are the harmonics? The harmonics are at pi and at minus pi. At pi, what is the Fourier series coefficient? You must extract the Fourier series coefficients like this. 2 pi times A1 is equal to pi. So what is A1? 1 over 2. 2 pi times A minus 1 is equal to pi. So what is A minus 1? No, it's again 1 over 2 because it's a plus. So 2 pi times A minus 1. This is 2 pi A1. This is 2 pi A minus 1. So A1 is equal to A minus 1 is equal to 1 over 2. And what is that? What does it correspond to? It's a cosine. So this thing is a cosine. What? What's the frequency? Pi. Cosine pi t. So this signal of rectangle plus cosine pi t would give you this Fourier transform. From the non-periodic part, you have some shapes. Okay, this is a sink shape, but it could be any other shape. They are just normal shapes. But from the periodic component like this, you come up with impulses like cosine. If it's a triangular periodic waveform, it will be something else. There will be many more impulses coming from triangle. Okay, so they can be combined as well. It may have a periodic part and an aperiodic part like this. A periodic part will correspond to a Fourier transform having delta functions, impulse functions. Okay. How much time do we have? Okay, now that we have seen this one, the trivial extension, it's not even an extension, it's a previous case of that. X of t is equal to cosine omega 0 t. What is the Fourier transform of this? There are two Fourier series coefficients for a cosine, and each one of them is equal to 1 over 2. So we have 1 over 2 times 2 pi times delta at the corresponding frequency. The first harmonic is at omega 0. So that's an impulse at omega 0. Plus a minus 1, which is 1 over 2 again, times 2 pi times delta. The other harmonic is at minus omega 0. So it's an impulse at minus omega 0. Like this. So this is quite simply the Fourier transform expression, which is pi delta omega minus omega 0 plus pi delta omega plus omega 0. All right. Now, an interesting signal and I'm going to solve it in two ways. This interesting signal is, let me give you a hint, it's a periodic signal. X of t is equal to k from minus infinity to infinity delta t minus kt. Do you remember the name of this? Impulse train. Impulse train. So this is an impulse train which is naturally periodic, and therefore it has Fourier series coefficients. Do you remember the Fourier series coefficients of that? Even if you don't remember, just apply the formula of Fourier series coefficients. And you will find it to be 1 over t, 1 over capital T, which says that ak doesn't depend on k. For all indices, the Fourier series coefficients are always 1 over capital T, whatever that capital T is. Now, what are we going to do now? So, what does the Fourier transform of that thing look like? A0 is here, and it's equal to 1 over capital T. So I have to multiply it by 2 pi. 2 pi over capital T, the first impulse. And then the second impulse, it's again value 2 pi over capital T at omega 0. What is omega 0? Omega 0 is the frequency. The period is capital T. What's the frequency then? 2 pi over capital T. That is omega 0. And then the same impulse at 2 omega 0, the same impulse at 3 omega 0, and it goes on to both directions. Minus omega 0, minus 2 omega 0, etc. It tells us that if it's an impulse train in the time domain, like this, separated by capital T, then the Fourier transform is also another impulse train, this time on the frequency axis. So the Fourier transform of an impulse train is an impulse train, because the Fourier series coefficients are never decaying, they are staying constant. So this also makes an impulse train. Now, if you solve it in a different way, like this, x of j omega is the Fourier transform of, let me indicate the Fourier transform with a calligraphic F and curly brackets. What are the items that we have? Several impulses. For example, they are delta t plus delta t minus capital T plus delta t minus 2 capital T plus etc. That is this infinite summation that I'm trying to represent. I'm just trying to represent a portion of that. But the Fourier transform of delta t is 1. The Fourier transform of delta t minus capital T is a complex exponential e to the minus j omega capital T. The other one is e to the minus j omega 2 capital T plus e to the minus j omega 3 capital T plus etc. Now, when you combine this thing, you can represent it in a summation form. Like this. So x of j omega is summation k from minus infinity to infinity e to the minus j k omega 0 capital T. Sorry, not omega 0, omega capital T. Right? When k is equal to 0, it is 1. When k is equal to 1, it is e to the minus j omega t, which is this way, etc. All this summation from k from minus infinity to infinity. This summation is the Fourier transform. Do we agree? Okay. It's true. This is the Fourier transform. And on the other hand, this x of j omega is also the Fourier transform. Let's write that one then. What is that? It is 2 pi over capital T summation delta omega minus 2 pi k over capital T. Because 2 pi over capital T, then twice of that, then 3 times of that. So omega minus 2 pi k over capital T. It's also the Fourier transform. So, which one is the Fourier transform then? The top one or the bottom one? Yes, that's true. Top one is the Fourier transform. But of course, the bottom one is also the Fourier transform. So what's going on here? Continuous, yeah?
Periyodik olmayan sinyaller için kullanılan.
Yeah, that's true. But nevertheless, it's the correct formula. You're right about that. We don't use it because we cannot evaluate that integral. Now we could evaluate that integral, so that's true. We don't use it because it's useless in many cases. It's not because it's incorrect. It is correct. And now we could evaluate it. So what's going on? What's going on is quite simple. These two are amazingly the same. I was truly impressed. I mean, I feel like Sheldon when I'm telling you this, because only Sheldon could be impressed by this equality, which is this. K from minus infinity to infinity e to the minus jk omega capital T is equal to 2 pi over capital T summation k from minus infinity to infinity delta omega minus 2 pi k over capital T. This equality is amazing because it is extremely counterintuitive. The left-hand side is consisting of sinusoids. We add up sinusoids, infinitely many of them, and we come up with a train of impulses. It looks impossible, but it's true. And as a matter of fact, it's a mathematical question. There are mathematical questions in the departments of mathematics which asks this. Prove that this is equal to this. And only the guys who know signals and systems and Fourier transforms could show their equality, because they correspond to the same inverse Fourier transform. Since they correspond to the same inverse Fourier transform, they must be the same signals. So this is one of the examples where the answer key in the exam question consists of two separate alternatives. If the student tells us this answer, then that will be a correct answer. If another student tells me this answer, then that will also be the correct answer. And in fact, they are the same, although they don't look the same. They look completely different, but they are equal. Okay? Of course, such things, or this example only appears in this question, impulse train question. For all the other questions, I still don't recommend that you evaluate the Fourier transform of the integration. Instead of that, please find the Fourier series coefficients and insert impulses. So this answer is technically preferable and easier for you to implement, because you know Fourier series. Please find the Fourier series coefficients and insert impulses over there and give me this answer. That would be easier for you. Don't try to give me this answer, right? Although it's correct technically. Okay, we can stop at this point. We'll continue tomorrow.